Bismillahirrahmanirrahim. Assalamualaikum. In this video, I'm going to continue on the DOE analysis by using ANOVA technique. Okay, before that, let's recap some of the notation that we are going to use. Okay, so the observation we denote as Y, and there is subscript there, so 1 represent the level 1 and the first observation, then Y21 is that the second level for the first observation, and so on. And then we have the total of the each level, so Y1 dot here means the total for the first level, and so on until we have the A level. And then for each level we have the average, so from the total we taking the average, which is we divide by the number of observation for each level, so we can get the average of each level. And then lastly we have the average in overall, means that we taking all the average of the each level, so here is the average of the overall observation. Okay, denote by Y bar dot dot. Okay, so Y dot dot here means that the total observation. Okay, the major step of the ANOVA requires us to calculate the sum of square. So this one you already come across in the chapter of simple linear regression. Okay, and then we determine the degree of freedom, calculate the mean square, so this one also already covered in the simple linear regression. And then we calculate the test ratio of F, and then we make conclusion, because ANOVA basically we want to test of the hypothesis in consisting more than one mean. So there are three types of sum of square that you have to know. The first one is the difference between individual observation and the grand average. Okay, so this is the observation. Then we take difference for the overall average just now. Okay, Y bar dot dot. And then difference between level average and the grand average. So this is the average of each level. So we take the difference between the level average and the overall. So we denote as tau 1. Okay, tau 1 referring for the first level. Okay, next we have the difference between an individual observation and the corresponding level average. So this is the individual, so the expected level average here, so that denote as epsilon I j. So we have different or error for each of the observation here. Okay, so also for Yij, which is the individual observation, minus the overall mean, so this one is equal to the level mean minus the overall mean plus the individual mean minus the level mean. Okay, so we can compute this way. So from that we can summarize that the sum of square total is equal to sum of square factor plus the sum of square error, whereby for this is the sums of the difference, so this is sum of the square difference. So then we have the factor. Okay, so the factor is the difference between the mean of the each level, and then we minus with the grand average. And then we have the error. So for the individual error means that for each observation we minus with the mean of the respected level. So this is the error, sum of error. So this is sum of square error. Okay, sum of square for total, okay, which is the measure of total variability in the data, because we measure for each observation with the grand totals. So this is the summation of the total error. And then we have sum of square of the factor, that is the sum of square difference between factor level average and the grand average, which is the overall average. So means that we calculate the difference between level. So the sum of square factor is approximately equal to n, which is the number of replicates. We multiply by the summation of the tau square. So whereby the tau is the ith level effect. So we sum up until all the level. So here we have until A level. Then for the sum of square error is the sum of square of difference between observation and their level average, means that it is different within level. Just now for SSF it is between level. So this is within levels. So it's given by SSE and it is approximately equal to the epsilon for each of the error, individual error square. And also SST is equal to SSF plus the SSE factor plus the error. So we get the total of SSE. SST, okay, total. Okay, so alternatively we can calculate the SST, F and E by using this formula. Okay, we'll get the same answer. So now we can use the A, which is the number of level, and also N, which is the number of replicates. Okay, so we can use either formula and you'll get the same answer. Okay, let's look at this example. Okay, so this as the same example actually. Okay, so you're going to calculate the SST, SSF and SSE for this data. Okay, given there are two types of machine, USA and Japan, so means that there is only one factor with two level. Okay, and then the response is process capability. So A is the number of levels, so we have two levels here, and then N is the number of replicates. So for each level we have 3 observations, so means that the replicates equal to 3. And then average for the first level, so we're taking average of 2.1 plus 2 plus 1.9 and then divided by 3. So we will get the average of the first level and also the average for the second level, and then average in overall. So this sum of square, we are going to use the formula just now. Okay, so we square for each observation and then minus the overall mean. Sorry, this is not overall mean, this is the total, overall total. Okay, y dot square. Okay, so this is the total overall. Okay, 9. So we total up the observation, we will get 9. And then the total in overall, we square the value, then divided by A times N. So A times N is 6. So this is the calculation. So we get the SST is equal to 1.54 and then followed by SSF and SSE. So use this formula. So since we already calculate the SST and then SSF, we can find the SSE by minus the SST with SSF. If the SSF is large, so means that the difference among the means or the different level is large also. Okay, so means that here if you refer to the SSF, because we take difference between the total of the each level with the grand total. Means that for large SSF, it indicate that the tau also large, okay, which is the effect of high level. So from that, the factor shows significant effect on the response. So usually for SSF, we taking standardized by divide the SSF with SSE, okay, in order to compare the effect of the each level or the level effect with the total error, okay, SSE. So from this proportion, we can compare to see how much variability is due to changing factor level, okay, and how much is due to the error. So means that is if the SSF is greater than SSE, so this proportion will be greater than 1. Okay, so if we refer to the previous example just now, okay, for this one, okay, so if we compute the proportion SSF divided by SSE, So we will get 37.5. And then for this example, if you compute the same thing, we'll get 0. Means that there is no effect on factor levels. So this one has effect. Okay, next step in DOE, we have to determine the degree of freedom. So we have to compute the degree of freedom for SST, SSF, and SSE. For SST, it is total. So total number of the observation, we minus 1. So the total number of observation is A multiplied by N. Number of level multiplied by replicate. So this is the case where we only have one factor. And then for degree of freedom for factor is A minus N. So A it is the total of the level minus 1. And then SSE is R, which is the number of run multiplied by N minus 1. So N is the replicates. So replicates minus 1 multiplied by run. So we get the degree of freedom of the SSE. So just now we know that SST equal to SSF plus SSE. So for the degree of freedom also the same. So this degree of freedom of SST is equal to degree of freedom of SSF plus SSE. So this is the equation for the degree of freedom. Referring to this example just now, so we compute their degree of freedom for the 3 SS sum of square. Then from that we compute the mean square. So mean square for the factor is SSF divided by its degree of freedom, and then mean square for error, sum of square error divided by its degree of freedom. So we can compute the mean square by using this formula for factor and error. But for the total, we don't have to compute the MS. Mean square for total, we don't have to compute. So because in order to find the ratio of F, we only need the mean square factor and mean square error. So you have to compute only for these two. And then for the degree of freedom also, we only refer to the degree of freedom of the factor and error. So B1, B2, because we are going to use the F distribution. So I already introduced the F distribution before this, before we learn the estimation topic. But we are not using in the estimation, we are using F distribution for the ANOVA. So for F distribution, we have 2 degree of freedom, V1 and V2. The test ratio here also can be calculated by using this formula, whereby from just now the ratio of mean square factor and mean square error, if we use the SSF and SSE and then the respected degree of freedom, so we can simplify by using this Q constant, which is this is the degree of freedom for here is the degree of freedom for the error, and then this is the degree of freedom for the factor. So we represent it as Q, which is constant. Lastly, we're going to make a conclusion from our hypothesis testing based on the test ratio. So if the test ratio is large, so SSF is large, because we can see that this SSF, if it is large, so means that the tau is also large, which is the effect of the level. So if the tau I is large, so it indicates that the factor significant effect, give significant effect to the response. So as usual in hypothesis testing, so this is the statistic the test statistic. So we need to have the critical value where we have to compare the statistic test whether it is fall into the radiation region or not. Here we call the critical value as the control limit given by F, okay, referring to the distribution that we use, alpha. So alpha also depend. Normally we will use 1% or 5%, and then B1, degree of freedom for the factor, and then V2 is the degree of freedom for the error. If the ratio test is less than the control limit, so we can conclude that the factor has no effect. Otherwise, if it is greater than the control limit, so we can conclude that the factor has significant. So this is the concern, okay, to make the conclusion on the hypothesis testing. So this is all the procedure or the step that we need to construct or follow in order to use the ANOVA test. So this is basically the F distribution. So actually, okay, this is skewed. We call it skewed to the right, just like the square chi-square distribution. So here it starts with the positive number, which is 0, and then it's getting larger here. So means that if the F naught or the ratio test is large, okay, because the number here start from 0 and then getting larger. Okay, so if the F naught or the test ratio is large, means that the area here will be very small. Okay, so let's say we compare this one and then this one. So this is very small area compared with this one. So this is where the P. So means that if the P is small, F naught is large. Whereby if the F naught is large, we conclude that the factor has significant effect on the response. So this is the case where we just simply find the P value from the test ratio value just now. Because normally for the before this, when you learn the hypothesis testing, we have the from the hypothesis testing you use the normal distribution or T distribution, right? And then we have the rejection region, and then the critical value here, and then we compare the test statistic whether it fall into this region or this region. So if it fall into this region, which is the rejection region, so we will reject the null hypothesis. Otherwise, if it is not greater than the significant critical value here, instead it is in this area, so we will not reject the null hypothesis. But in this case, we can also find the P value from the test ratio, which is the F naught. So then we can know whether the P is small or large. Okay, so then we can conclude whether the F naught is large, and then it's indicate that the factor it is significant or not. Okay, I will stop until this, and then in the next video we will go through the example and the calculation from the case study. Okay, we refer to the previous example, so then we try to calculate all the statistics, and then we go through the step by step of the ANOVA. Okay, bye then. Assalamualaikum.